Hey, this is Math 6, Unit 5, Lesson 14, using operations on decimals to solve problems. So we have lots of fun problems for you to do to solve together with decimals. All right, so here we go. So first we have some estimates. For each expression, choose the best estimate of its value. So we have 76.2 divided by 15. So think about this as being like in the 70s divided by 15. We're probably looking at something that there are at least probably 5 groups of 15 inside of there, right? It's not going to be half a group, that'd be like 7. And 50 is way too big, so that makes the most sense there. With these numbers here, you have 56 about divided by 48. Those numbers are fairly close together. So chances are there's not a whole 10 48s inside of there. There's probably more like 1 is the best answer. 100 is just crazy talk. And here we have 20 divided by 124 divided by 20. Right, so this is like 120 right there divided by 20. We know that 2 goes into 12 about 6 times, but we're talking about 20, so we're probably looking at more like a 60. So just looking at those, see if you can make those connections to see what's going to make the most sense. Let's look at our lesson for the day, really. Applying division with decimals. Your teacher's going to assign you a problem, problem A or problem B. Work together as a group to answer the questions and be prepared to create a visual display to show your reasoning with the class. So either you have problem A, which is here with 2 problems, or B. Okay, and you want to look at your problem and solve both pieces and then be ready to explain to the class how you got what you got. And then problem B, the same thing. Okay, so decide if you're an A or a B. Partner maybe on the left is A and the right is B, however you want to do that, and then compare your answers and see what you ended up getting. Alright, so I'm going to look at A first of all. It says a piece of rope is 5.75 meters in length. If it's cut into 20 equal pieces, how long will it be? So we're taking that bit of rope, 5.75, and we're dividing it into 20 equal pieces. So I'll put the decimal point up there right away. 20 goes into 5 0 times. It goes into 57 about, not 3 times, more like 2 times. 3 would make 60, so I get 40 here. We subtract 7 and 1. We're going to bring down the 5. And so does it go into 175? Well, it goes into 80 would be 9, so we have to probably go with 8 for 160. And we have a remainder of 15, so we're going to add a 0 to keep on going. We're not done yet. Does it go into 150? Nope, it doesn't. Not equally. So 7 gives you 140, so we have 10 left. We'll bring down another 0 at least, have 100. And 20 goes into 100 5 times. So how long would each piece of rope be? About 0.2875 meters in length. Okay, that's about how long each one would be. Now if you cut that into 0.05 meter pieces, how many pieces can there be? So this was just making 20 equal pieces, and that's how long it would be. Now we want to know if the pieces are that long, how many can we make? Alright, so a little different problem here. This is going to be to take our original length, 5.75, and we're dividing it by 0.05. Okay, so we can move the decimal there, 2 spots there, and put it up right away if you choose to. So now I'm dealing with 5. There's one group of 5 and 5, so that becomes 0. Bring down this 7. How many groups of 5 and 7? 1. So we subtract. Bring down the 5. How many groups of 5 and 25? 5. And we have remainder 0, so we'd say that you could make 115 pieces that were that length out of this amount of rope. Okay, partner B, let's see what you did. So the tortoise travels 0.945 miles in that many hours. How many miles per hour is it traveling? So we're looking at doing what? Miles divided by hours. So that's our miles and hours. So we're going to do 0.945 divided by 3.5. That's our miles divided by hours. Okay, that's miles per hours. So we have 0.945 here. We divide it by 3.5. Move the decimal over 1, move it over 1, and put it up top right away. 35 goes into 9 0 times. 35 goes into 94 about 2 times for 70. 4 minus 0 is 4. 9 minus 7 is 2. Bring down the 5. And 35 goes into 245. Well, 3, I think about this way. I think about 3 goes into 24 about 7 times. So 7 times 5 is 35 with a 3. 21 plus 3 is 24. That worked out nicely. No remainder. So we would say 0.27 miles per hour is the speed that it's traveling. At that rate, how long would it take it to go 4.86 miles? Okay, 4.86 miles. So we're going to find out. So we do 4.86 miles, and then we're going to divide that by 0.27. Oh my goodness. Okay, and we're going to move that 2 spaces, move it 2 spaces, and right up away. 27 goes in here 1 time. So we have 21, bring down to 6, and it's going to go in there about 8 times. 8 times 7 is 56, and then 16 plus 1 is 21, remainder is 0. So how long would it take to go that long? It would take 18 hours. That's a long time. So they do not get too far too fast, do they? Let's look at activity number 3. It's a fun one here about distance between hurdles. It says there are 10 equally spaced hurdles on a racetrack. The first hurdle is 13.72 meters from the start line. The final is 14.02 meters from the finish line. The racetrack is 110 meters long. Draw a diagram that shows the hurdles on the racetrack and label all the known measurements. Okay, so we know there's a starting line, and we know there's a finish line. So we have our start and our finish. We also know that there are 10 equally spaced hurdles. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hurdles. Here's hurdle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hurdles. We know the distance between the first hurdle and the starting line is 13.72, and the distance between the final hurdle and the finish is 14.02, and we know that the whole thing is 110 meters long. Okay, so that's what we know so far. So how far are the hurdles from one another? It said that they were equal distance from one another, or they're spaced evenly, or spaced equally, right? So what we want to do is we want to say, well, I want to find out what the space is here. Okay, if I'm looking at it like this, I'm wanting to find out this space is what I'm dealing with here, and I know that each one of these segments is identical, right? So this and this and this and this and this, these are all the same. Okay, I know the picture's not quite the same, but they're all the same. And I can make the other one pink just so you can see it's alternating just for fun, just to make it pretty. Alright, but how much space am I dealing with here? I began with 110 meters, right? But I need to remove those part from our equation because they don't really make a difference for what's in that space there. So I'm going to do 13.72, and I'm going to add to it the 14.02. Okay, the distance from the beginning and the finish there. So we have 4772, and let's subtract that from the total distance to see what kind of space the yellow is going to be. So I'm going to borrow 10, borrow 10, borrow 10. 10 minus 4 is 6, 9 minus 7 is 2, decimal goes there. 9 minus 7 is 2, and then 10 minus 2 is 8. So I know now that this yellow distance right here is actually 82.26 meters. That's how much space we have there. But how many segments are going to be? You might think 10, but let's look at them. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces in between the 10 hurdles. So I'm going to do the 82.26 divided by 9 to find out how much space is inside of one hurdle, or between 2 hurdles. So we do 9, 82.26, decimal point can go up right away because that's a whole number. 9 goes into 8 0 times, it goes into 81 9 times. 9 times 9 is 81. Subtract, we have 1 there, bring down the 2. 9 goes into 12 1 time. We subtract, 12 minus 9 is 3, bring down the 6. And 9 goes into 36 4 times, and we have no remainder, which makes sense. We wouldn't want a remainder if this is going to be evenly spaced. So the distance between each hurdle then is 9.14. 9.14. And we could write that in all of them, but you get the idea. Okay. Now, still with the hurdles here, it says a professional runner takes 3 strides between each pair of hurdles. The runner leaves the ground 2.2 meters before and returns to the ground 1 meter after. About how long are each of the runner's strides? Okay, so let's just do a little picture here. We have basically, let's say this is hurdle number 1 and hurdle number 2. Okay? Okay, so here's hurdle 1, hurdle 2. What we know is that they leave the ground 2.2 meters before, okay, and they land on the ground 1 meter after. Okay, so this is kind of in the air. They're in the air for a total of 3.2. They're in the air, which means that if we think of it this way, then that if he's going to the next spot, this is a 2.2 as well, so it leaves this space for the running, right? Landing 1 meter in, takes 3 strides, and then jumps with 2.2 over. Okay, so there's a total of 3.2 of this distance then between hurdles that the person is actually in the air. So what was that distance before? We said it was 9.14 was the distance between here and here. So let's then remove the time that's spent in the air, or the space in the air, which is 3.2. So we have 4, 8, 11 minus 2 is 9, 8 minus 3 is 5. So we have 5.94 is the distance for how many steps? For 3 strides. So we'll take our 3 strides, and we're going to see how long each stride is going to be if you're only having to go 5.94 meters. So 3 goes into 5 one time. 5 minus 3 is 2. 3 goes into 29 9 times. 27. Got a 2 there. Bring down that 4. And 3 goes into 24 8 times. So we would say that each stride is about 1.98 meters in order to get 3 in there and have enough time for takeoff and landing. So a fun little problem. Very fun. Okay. Our next problem here, another one. A little optional, so you may have done this in a class or maybe not, hard to say, depends on what your time looked like there. It's a good problem, but it is rather lengthy. It requires lots of calculations here, but again, it's a good problem. So it says a full tennis court used for doubles is a rectangle. All the angles made by the line segments in the diagram are right angles. The net partitions the tennis court into 2 halves. Is each half a square? Now to be a square, you'd want to make sure that the length and the width are the same, right? 1 and 1 or 2 and 2, whatever it's going to be. So the question here is, if the net line is here, do I end up with a square? Okay. So let's first of all take a look at the baseline. The baseline has 1.37 right there, has 8.23 right there, and a 1.37 there. Meaning the total distance of the baseline will be the sum of these 3 parts. So I have 10 plus 7 is 17. I have 3, 4, 5, 6, 7, 8, 9 there. And I have 8, 9, and 10 there. So the baseline is 10.97. Now the length of the court, it's going to be not 23.77, but 23.77 divided by 2, because the net cuts this entire length in half. So we're going to divide that there. 2 goes into 2 one time, which is 2. We bring down the 3. 2 goes into 3 one time. 1 times 2 is 2. We subtract, and we have 17. Decimal there. 2 goes into 17 8 times for 16. And we do another one, which is 17. And we have, goes in there 8 times, which is going to be again 16. We bring down a 0 this time, and 2 goes into there 5 times. So the baseline is 10.97. Oops, sorry, ran out of space again. And the length is 11.885. Are those two values the same? We would say no. So we would say it's not a square. Now the two sides are equal, but these dimensions don't make a perfect square. Okay. Is a service line halfway between the net and the baseline? So is this halfway between here and here? Okay. So we know that the whole length from the net to the baseline is 11.885. It tells us the service line is already from the net, here's the net, right, to the service line is already 6.4, and the baseline is here. Oh my goodness, I need more space. So if the whole thing is going to be 11.885, then if this is halfway, then this should also be 6.4 if it was halfway. Now when you just look at that, you already can tell 4 plus 4 is 8, 6 plus 6 is 12. That's too big, which tells you this is not going to be halfway. Can we figure out what it's going to be? Sure. The distance actually right here is not 6.4. It'd be what's left after you do 11.885 minus 6.4. So we have 5.8.4, and we have 5.485. 5.485. So even from here to here, this is not halfway from here to here. Okay, this is a bigger distance than what's right there, interestingly enough. Okay, so nope, it's not halfway. Now, the next question's a little bit trickier, take some time, okay? So maybe, again, something your teacher's not going to do. If you want a little extra practice, this is great practice. It says, lines painted on a tennis court are 5 centimeters wide. A painter made markings to show the length and width of the court, then painted the lines to the outside of the markings. Did the painter's mistakes increase or decrease the overall size of the tennis court? And explain how you know. Okay. So we're going to say this. If you make markings like this to be the dimensions of the court, and then you paint lines on the outside of the dimensions like this, even if it's 5 centimeters, you have now increased the overall size of the court. Because in tennis, okay, the lines are considered to be in, so they count as part of the court. Okay, if a line was out, then it wouldn't make a difference, but because a line is in, you've now increased that. So the question B would be, by how many square meters did the court size change? Okay, so think about the court size. We know already that the length is 23.77. We know that the width is a 10.97. We have a length here and a length here. So again, 23.97 or 77 and 10.97, which we knew from the last problem. Now we're adding a 0.5 centimeter length there, 0.5 there, 0.5 here, 0.5 here, and then we have these little square spots which we're also going to have to include. So all these extra areas are going to be increasing the overall square meters of the court. Okay, and again, these lengths are all this is 5 centimeters. We make that 0.05. So this little space right here is found by doing 10.97 times 0.05, which when you multiply that out, we end up with we have 5 and 3. 45 plus 3 is 48, and then 5. Okay, so this is 1, 2, 3, 4 decimal there. Okay, so this has a value of 0.485. We can call this the blue one here. So this blue one here is 0.5485, and so is this one. So we actually have 2 of those. So we're going to take that and we're going to add it to another one, 0.5485. 10, carry the 1, 17, carry the 1, and 9, and 10. So the area we've added in the blue is already going to be 1.097 square meters increase there. For this part here, we take the 23.77, also multiply it by the 0.5, and when you multiply that out, you end up with 11885, and we have, in this case, 1, 2, 3, 4 behind the decimal, 1, 2, 3, 4. So we have 1.1. Okay, we can call this our pink section. Pink section, pink section. There are 2 of them, so we add them together. And 5 plus 5 is 10, we carry the 1. 16 plus 1 is 17, carry the 1. 17, carry the 1, and 3, and decimal, and 2. Okay, so the pink section has 2.3770 extra meters, but then we have these little squares. We have 1, 2, 3, and 4. Now the length and width of those squares is 0.05 times 0.05, because that's the length and the width. 5 times 5 is 25, and that's it. But we have 4 behind the decimal, so we have 1, 2, 3, 4. Alright, so that's the area of one square, but we actually have how many of those squares? We have 4 of them, so I can multiply that by 4. 5 times 4 is 20, carry the 2, 4 times 2 is 8, plus 2 is 10, and then we have 4 behind the decimal, so we have 1, 2, 3, 4. So our squares have a combined grand total of 0.01, which means that in total, the extra space is 1.097 plus 2.377 plus 0.010, like so, which means we have a total of 14, carry the 1, 16, 17, 18, carry the 1, 4, decimal, 3. So we have that many extra square meters because of the extra paint on the outside of the court. So that's how much you increase the whole court by. A lot of work, I know. So again, your teacher may have skipped that one. Maybe I should have too. But good problem. So if you wanted to try it, that's what I got for my answer. Good luck on yours as well. Alright, so 14, summary. Diagrams can help us communicate and model mathematics. A clear label diagram helps us visualize what is happening in the problem. Okay, and so with sports, we see great examples of how diagrams can help us solve problems, which we did with the hurdles, we did with the lines, the tennis court. Those are always cool, and again, because you're doing a sports, accuracy of measurement really does matter. You want to make sure that things are equal and even for both players when you play those games there. Alright, that'll do it for the lesson. I'm going to pause there, let you work on the homework, and then we'll come back and check it together in just a couple minutes. Alright, a roll of ribbon was 12 meters long. Diego cut 9 pieces of ribbon that were 0.4 meters each to tie some presents. He then used the remaining ribbon to make some wreaths. Each wreath required 0.6 meters. For each question, explain reasoning. So a lot going on here. We have 12 meters ribbon. He cut 9 pieces, right? He cut up in 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces there that were 0.4 each. Then he had some left over. He wanted to make some wreaths. Each wreath is going to be 0.6, so how many times could he chop that up? So how many meters were available for making wreaths? Well, we know that he had 9 ribbon that were 0.4. So we do 0.4 times 9, and that's going to give you 36. Decimal moves over there. So 3.6 is what he had used for just the ribbon to tie presents. So we need to subtract that from what he started with, 3.6. And we borrow, and we have 4, and 11 minus 3 is 8. So he has 8.4 meters left for making the wreaths. Now the wreaths each take 0.6. So we want to find out how many 0.6 are inside of 8.4. So we move that over one spot, move that over one spot, and put it up top right away. 6 and 8, there's one group of 6 and 8. And then bring the 4 down, and there are 4 groups of 6 and 24, and 0, so we can make a total of 14 wreaths. So lots happening in that problem. It's a great problem to kind of get used to because that's the kind of work you're going to see as the year goes on. The Amazon rainforest covered 6.42 million square miles in 1994. In 2014, it covered only over 59th as much. Which is closest to the area of the Amazon rainforest? Explain how you know. Okay, so we can see here, even though it has 50, we're not saying it's half of that, right? We're saying it's 50 out of, basically 50 out of 60, okay? So 50 out of 60 is what we're saying, or about 5 out of 6, if you kind of want to reduce that down. So we know it's going to be less than 6.42, okay? But we're not talking about a substantial amount less. First of all, this one is definitely less and not by very much at all. So could it be an answer? It could be, but hard to say. This one is less, and again, not by much less, so it could be as well. This one seems to chop off quite a bit, a lot, and a ton. I'm thinking more like, just out loud, I would probably not lean towards these just by how they look, and it might be somewhere more in this range. Now, if we're talking about 5/6 of about 6 million, right? 5/6 of 6 million, okay? See, the 6 reduces to 1 and a 1, and so I'm left with 5 times 1, which is somewhere about 5 million. Again, all estimating, right? So which answer is closer to 5 million? We would probably go with something like the 5.4. That probably makes the most sense without calculating the exact area. That's about right there. Okay. The next question. To get an A on our math class, Jada needs to have at least 90% of the total number of points possible. The table shows Jada's results before the final test in the class. So let's take a look at this. She wants an A, she needs 90%. Okay. So this is what she has before the final. The final is going to happen here, and we don't know what that's going to be yet, right? So there's no final score yet. We don't have scores there. So does she have a 90% possible before the final? To figure that out, we want to add these up and then see what the possible is going to be. So we have 141, 87, 81, and 91. When we add these up, we see that she has 7, 8, 9, 10, carry the 1. We have 16, 26, 30, carry the 3, and we have 400. So she has right now 400 points out of how many are possible? 150, 100, 100, 100 out of 450. So far she has 400 points out of 450 points possible. When we do the math on that, okay, what we find out is that, in this case here, did I do this wrong? 7, 9, 10. Yeah, 10. Oh, that's funny. Oh, yeah, okay. So she has a total of 400 out of 450. Okay. Now, as a division problem, we could say, well, what is that going to be? And you can use a calculator or whatever it might be. But to get an A, she needs to have 90% of this. Well, 90% is 0.9. Let's do 450 times 0.90, 90%. So to have full credit, or have an A, she would have to have how many points? That's 45. 36 plus 4 is 40. She's going to need to have, 2 by the decimal, 405 points. She has 400, and then she needs 405 at that point to have an A. So she's just below an A, right? Because 400 points is less than the 405 needed to be 90% an A. She's close. Jada thinks if she gets 92 out of 100 in the final test, she will get an A in the class. Do you agree? Well, that's going to change what she has to be 492 out of, and then we add 100 to the total, 550. So is that close? Well, let's look at it this way. I don't really want to do 492 divided by 550. I'll do 550 times 0.9, which is 90, right? 0, 45. 45 plus that is 49. Okay, 1 decimal. So to have an A, she needs 495 points. What does she have? 492. Does she have a 90%? Nope, she's close, but it's still a B+. Okay, so could the teacher be nice and round up and say 3 more points if possible? They could. They could leave it there and say it's a B+. It's how it works. It's math. They could do that as well. So you never really know. Okay, and then sometimes, and like at least at our school, sometimes a final is worth a larger percentage than a regular test. So instead of having being 100 points, sometimes a final can be worth like 200 points or 300 points. Also, the other thing is, at our school, the homework is not as valuable as the test itself. So this actually has a percentage compared to that. So your test grades equal 70% your total grade, and that's 30% total grade. Right now, she's getting a lot of bonus points for doing her homework. And at our school, the points come from showing what you know on your assessments. But that's a whole other story. So let's move to number 4. Find the following differences and show your reasoning. So we have 0.151 minus 0.028. Can't do 1 minus 8, so I have to borrow. 11 minus 8 is 3. 4 minus 2 is 2. 1 minus 0 is 1. So you have 0.123. 0.106 minus 0.0315. Add a 0 up there to help us subtract. We're going to have to borrow. So 10 minus 5 is 5. 5 minus 1 is 4. Can't do 0 minus 3, so I borrow from there. 10 minus 3 is 7. 0, 0, 0.0745. And then finally 3.572 minus 2.6014. 0 minus 4 I can't do, so I'm going to borrow. I have 10 minus 4 is 6. 1 minus 1 is 0. 7 minus 0, can't do that, I borrow. 15 minus 6 is 9. Decimal point, so we have 0.9706 there. Alright, we're going to find some quotients here for this last one, and that'll be our last one for this lesson, and for me, the last one for this unit as well. Alright, so here we go. We have 24.2 divided by 1.1. Move the decimal over, move it over, and put it up top. 11 goes in 24 2 times, so it's 22. We subtract, bring down the 2. 11 goes to 22 2 times, and we are done with that one. So 22 for this first one. Over here we have 0.4 going into 13.25. Move the decimal over 1, move it over 1, and put it up top. 4 goes into 13 3 times for 12. Bring down the 2. 3 goes in there 3 times for 12. Bring down the 5. It goes in there 1 time with 1 remainder. Add a 0. Bring it down. 4 goes into 10 2 times. So we subtract and bring down another 0. 4 goes into 25 times 20, and we have a solution there of 33.125. And then finally 0.08 going into 170.28. Gonna move it over 2 spaces, move it over 2 spaces, decimal point up right away. So 8 goes into 17 2 times for 16. Bring down the 0, goes into 10 1 time for 8. Bring down the 2 this time, and it goes into 22 2 times 16. Bring down the 6. Alright, bring down the 8 now. It goes into 68 8 times for 64. We have 4 left over, bring down a 0, and we have a 5 right there for 40 with no remainder. So our final answer here is 2128.5. Alright, that is it for that lesson, and that is it for our unit. Good luck, and we'll see you in Unit 6.